Good morning, everyone. We'll start our either Q&A session or just some additional problem review. Does anybody have any specific questions for me this morning? So the upcoming midterm is over chapters 3 and 4. Roughly, half the questions, about 10 questions from chapter 3, 10 questions from chapter 4. Should be pretty similar in setup to the real exams, of course, with different questions. So it's pretty similar to the practice exams. So hopefully you guys are looking at the practice exams just to get a sense of how you might do in the real test, and then using things like daily quiz questions, questions in the textbook to help you review. Okay, so the first 2 pages of questions today just come from the chapter 4 review packet that's in the lecture slides area. So we'll take a look at the final 2 pages from that packet first here today. So we're asked about the net ionic equation between iron 2, SO4 3, and KOH being mixed, but we're told aqueous solutions of these salts. So we're told we have aqueous solutions. So we kind of know already that I'm starting to write my reaction between Fe2, SO4 3, that I know that this is an AQ from what's told to me in the problem. Like, I don't have to even think solid versus AQ because I'm told we have an aqueous solution of it. So therefore I have to know that it must be water soluble. And it is. Like, if I think about the solubility chart for sulfate, iron is not one of the exceptions. And then I have KOH, which of course is also AQ from what I'm told in the problem and also from what I know about hydroxide ion. And then what we're considering is the exchange reaction. We can imagine swapping the iron and the potassium. So we'd get KSO4, so it'd be K2SO4, because SO4 is a 2 minus, so of course I need 2 of the K pluses. I don't need the parentheses around the SO4. Anything containing potassium is water soluble, so that should be an AQ. K plus is not an exception for sulfate, so I know that's an AQ. And then the other product would be the iron 3 plus. Now, how do I know it's 3 plus? Well, I know that's the right balancing of charge. So from nomenclature, would hopefully have named Fe2SO4 as iron 3 sulfate, so it's iron 3 plus. And then pairing up with the hydroxide ion, which is a minus, and so that'll take 3. So we get FeOH3, and then that should be the insoluble precipitate. Now, when I start thinking of my net ionic equation, I might think the full ionic equation first. To write the full ionic equation, I have to address each of the sort of formulas that I've written in the full molecular equation. The first equation we wrote, we call that the full molecular. Full molecular because the water-soluble ionic compounds really don't exist as those ion-paired, maybe what looks like molecules that we wrote in the formula. Fe2SO4 would really look like 2 Fe3 plus ions, and then the 3 SO4 2 minus ions, and then the KOH, which I didn't balance, but we'd put a 3 here, probably a 2 there to balance the 2 irons. Probably going to need to double things here because then I need 3 here to balance the sulfates to get 3 sulfates. And so that's going to kick me to having 6 potassiums, which means that I'm going to need 6, or not 6, but yeah, 2, that was right before, but 2 FeOH3s. And so I have 6 OH minuses on both sides. I have 6 K pluses, 2 irons, and 3 sulfates. So I probably should have balanced that full molecular before moving on to the net ionic, but that lets me see I have 6 K pluses, 6 OH minus ions. If you know how to name a molecular ion, then that ion stays intact. Like when I know it's potassium hydroxide, then it's going to be hydroxide ion and water that forms. And then we're going to have the products being the 6K plus the 3 SO4 2 minus ions, and then the 2 FeOH3s remain intact as that solid precipitate. So I only end up with the K plus and the SO4 2 minus ions as being the exact same form on both sides of the equation. So those would be what I call spectator ions. They watch the reaction. They're not changed during the course of the reaction. So then we can cancel them out from the net change. So the net reaction to the net ionic equation would be the 2 Fe3 plus the 6 OH minus go to 2 FeOH3s. But then I notice that for my net ionic that I can divide all these by 2 and get whole numbers. So I can reduce that down just to Fe3 plus 3 OH minus forms the FeOH3 solid. And then I neglect writing AQs for the ions just so I don't have to write AQ like 50 times. And so technically these should both be AQs. Just like everything with a charge in the full ionic equation would really be an AQ as well. So that should lead us to answer B. So the idea of like writing equations is really to try to see, is there a net change? That's why we kind of ask these net ionic equation reactions, is so we can spot what that net change is and write that particular chemical reaction. Okay. Let's move on to that second question. So we have 0.15 moles of lithium chloride added to a 250 milliliter volumetric flask, and we fill with water. We're dissolving the solid to get to that 250 milliliter point. And then we have a pipette transferred 4 milliliters of that solution that we prepared to a new 50 milliliter volumetric flask. It's then filled with water and the solution's diluted. So we have a couple of steps here. We're making one solution and then we're diluting it to make a second solution. So let's calculate the concentration of lithium chloride in that initial solution. Let's call that lithium chloride initial, and that's the lithium chloride concentration in the first solution. Now concentration or molarity is just moles, so I got 0.15 moles of lithium chloride per 0.250 liters of that solution. I guess it would just be 0.25, I think. The sig figs are a little bit tricky here, but we're gonna end up just with 2, so I don't wanna get too bogged down by thinking too much about sig figs here. If I have my calculator with me. So 0.15 divided by 0.25, 0.60. And so I can write that 0.60 M, capital M just means mole per liter lithium chloride. So 0.60 moles of lithium chloride per liter of that solution. And then I'm going to do what could be like an MIVI equals MFVF problem if we know that equation. That's actually not on our equation sheet, so we'd have to remember that equation. But we're just kind of using the idea that molarity is equal to moles over volume, so that moles could be equal to molarity times volume. And then during the course of a dilution, we're not changing the moles of the solute, we're not changing the N. So like our initial molarity, our initial volume is equal to our final volume times our final molarity, because those are equal to also the moles of the solute. Whether or not you know how that equation is derived, if you know the equation, you can use it, apply it. If you forget the equation, you can either use the idea of molarity in the problem. We could calculate the moles of lithium chloride in the 4 milliliters of that solution that were withdrawn. So we could just use a concept of molarity to help us through this problem too. So I could just address, taking this times 0.0040 liters of the solution, that's 4 milliliters, seeing how many moles that corresponds to, then dividing the moles by our new volume as approach 1 just from the definition of molarity. Or we can apply the MIVI equals MFVF, and then this is my MI, the VI. I can just use the 4 milliliters without converting. And then my final volume is what we dilute that solution to, 50 milliliters. And so we can solve for our final molarity as our MIVI divided by VF. Just solving for VF here, or excuse me, solving for MF. And so that should be 0.60 M times 4 milliliters divided by 50 milliliters. And so as long as the VI and VF are in the same unit, I don't have to bother converting to liters. I can leave them both in milliliters. So 0.6 times 4 divided by 50 is 0.048. So we've reduced the concentration by diluting with water, is the idea. So again, this problem here, you could use a concept of molarity or you can use the equation. Another question we could have just gets at the concentration of ions. Like, so what's the molar concentration of chloride ions within a solution of 2.0 M iron chloride solution? Now, iron chloride in water is really Fe, it's not right to 2 yet. It's really Fe 2 plus, and 2 chloride ions. So if I have a mole of FeCl2 in water, I would have 2 moles of chloride ions. If I had 2 moles of lithium chloride ions per liter of solution, I'm going to have 4 moles of chloride ions per liter of that solution. So the concentration of the chloride ion, I could start and just write it very simply. There's just 2.0 moles of FeCl2 per liter of that solution. Then every 1 mole of FeCl2 that is in that solution releases 2 moles of chloride ions into the solution. Of course, because we have a water-soluble ionic compound that dissociates. So of course that would be 4.00 molar. Sometimes we ask for like the total ion concentration. If I had said instead, well, what would the total ion concentration be? Remember, the brackets just says what's the molarity of what's inside. So what's the moles per liter of the total ions in the solution? Well, we can start with the 2.0 moles of FeCl2 per liter of that solution. And then every 1 mole of FeCl2 gives us 3 moles of ions in solution. So that would be, of course, 6.0. So you could calculate specific ion concentration. You can calculate total ion concentration. The more ions a mole of a compound has, the greater the ion concentration. So we're asked in the last question on this particular packet, again, this is a chapter 4 review packet and lecture slides. We're asked to write and balance the oxidation reaction between aluminum metal and nitric acid, and then we're asked a stoichiometry question about it. Okay, so aluminum metal will be Al solid, HNO3. Now we could use the activity series if we needed to, like the H plus links up to H2 gas, and then the aluminum links up to aluminum 3 plus, it's common ion. So aluminum here, when it reacts, is going to form aluminum 3 plus, and then H is going to return to H2 gas. So we're going to form H2 gas. And then my balancing, I compare aluminum up with the nitrate ion. That should be water soluble because all nitrates are water soluble. And then if I need to balance here, if I put a 3 in front of the HNO3, I'm going to have an odd hydrogen count. So why don't I double here to give me 6 nitrate ions. So that gives me a 6 in front of HNO3, and then a 3 in front of H2. And then I'll need a 2 in front of aluminum to balance 2 aluminums on both sides. So again, my thought would be without the 2 in front of the AlNO33, then I could have put a 3 in front of the HNO3 and saw that that's 3 H's, not going to balance with the H2 on the other side. So hence we're just basically doubling everything. Okay, so now once I have the reaction written in balance, I can then get at the stoichiometry question. It's saying how much 0.50 mole per liter HNO3 is needed to fully dissolve 27.0 grams of aluminum. So 27 grams of aluminum, how many liters? Let's see if we can use dimensional analysis here. So I'll start with my 27 grams of aluminum. Now it looks like I need to do a mole to mole conversion. So usually in a stoichiometry problem, you're going to have a gram to mole or a liter to mole conversion with the molarity. So aluminum, molar mass, 27.0 grams per mole. So that's 1 mole of aluminum. And then according to my balanced reaction, for every 2 moles of aluminum that are present, I need to add 6 moles of HNO3. And now my solution of HNO3 is 0.500 moles of HNO3 per liter of that solution. And sometimes if I don't think of what the M means and write it out or picture that it's the moles of that thing per liter of that solution, I might miss this step here. But this is my next conversion factor, but I need to put this down here. I need to put the 0.500 moles of HNO3 are present in every 1 liter of that solution, because that cancels my moles of HNO3, cancels the moles of aluminum, cancels the grams. So if I'm applying my dimensional analysis, I need to divide by the molarity here. I probably can only see that if I explicitly write out M as mole per liter, and it's moles of whatever the solution is. So if it's 0.500 M HNO3, it's 0.500 moles HNO3 per liter of that solution. And so that allows me to calculate the volume of the solution in liters. And so it should work out to 6. So this will be 6.00 liters. So we have 1 times 6 divided by 2 is 3, divided by half would give us 6 liters. Okay, so we can solve the stoichiometry problem, just it kind of mixes a thought of chapter 3 problem, but now using that unit of molarity. So molarity times volume is moles, just like grams divided by molar mass is moles from chapter 3. All right, before we get started in chapter 5, I pulled a couple of chapter 3 questions. I haven't seen a lot of chapter 3 review in a while, so I thought why not just pull a couple chapter 3 questions. And again, hopefully you guys have seen or will take the practice exams, and if you need extra help, daily quizzes can help. But this is a chapter 3 review from the daily quiz area. The full quiz packet has a video solution on Carmen. About half of the daily quizzes have video solutions, so you can check the video solutions if I don't get through all these this morning. But I have a couple circled that I wanted to get through. So number 6 in that packet, the mass percent of carbon and cobalt-3 carbonate formula given. We usually won't give you a lot of pure nomenclature. That nomenclature is chapter 3, chapter 2. We already tested you on that. The upcoming exam, not intentionally going to be cumulative. There may be concepts that are helpful to remember, but we're not going to directly quiz you and test you on naming again. So we see the name and the formula here. But the percent carbon in this formula would just be equal to however many carbons there are in the formula. So there's 3 carbons. The mass of a single carbon is 12.1 AMU. I could write grams per mole, because 12.01 AMU or grams per mole for carbon are fine. Those are the same numerical values. So I'm either going to write the AMU per single atom and write that mass out here and then think of the formula weight of the whole molecule in AMU, or we could write the gram per mole in. It's going to be the exact same math. So I have 3 carbons in the formula, and then I need to take the sum mass of 2 cobalts. So cobalt is 58.93. So times 2 plus 12.01 times 3. And then plus 16.00 for the O, and there's 9 of them. So I get the formula weight of the whole unit is 297.89 AMU times 100%. I get 12.1%. The next question down, how many nitrogen atoms are present in 4.72 grams of magnesium nitrate? So my thought is to tackle this with the dimensional analysis step. So I'm going to start with my 4.72 grams. Sometimes you'll see the molar mass given as M equals. If you see that in a problem, that's the molar mass of the compound. Sometimes we'll do that. We'll do that predominantly more after this midterm, because this midterm we're supposed to be calculating molar masses. So you'll see a few problems intentionally want you to calculate the molar mass to make sure you know where to get that information from, because that's a key part of chapter 3. But we're just going to magnesium's mass in the periodic table. So 24.31 plus 14.01 for nitrogen times 2 plus the 16.00 for oxygen times 6. So I get 148.3. Now, what I need to do here is then either think how many moles of nitrogen are present per mole of this compound, that's one thought, or I could say how many units are there of magnesium nitrate per mole of magnesium nitrate. So I'm trying to get nitrogen atoms. So I can take one of two steps here. I can either say for every 1 mole of magnesium nitrate, how many moles of N are there? And it would actually be 2, not 1, because there's 2 moles of nitrogen in 1 mole of that formula. There's 2 N's in it compared to 1 mole of magnesium nitrate. Or we can do for every 1 mole of magnesium nitrate, there's an Avogadro's number of MgNO3 So like units of that formula. And then for every unit of the formula, there's 2 N's. Or for every 1 mole of nitrogen, there's an Avogadro's number of N atoms. So if I'm finishing off the top step, I'd say for every 1 mole of N, that would correspond to 6.022 times 10 to the 23 N atoms. And if I went the bottom step, I'd just say for every 1 MgNO3 unit, that there's 2 N's. So you see it's the same math. It's times 2 for the 2 N's, then times Avogadro's number. So it should be a big number. All the choices are big, so it doesn't really help narrow it down, but it should be a large number of nitrogen atoms. So if I go 4.72, divide by that molar mass. I'm going to hit equals just to see that I have 0.032 moles, so a pretty small number of moles, and then times 2, and then times Avogadro's number. So that's 3.83 times 10 to the 23. So either direction makes sense, and we can use either to calculate the moles of N in the sample first and then convert to atoms, or we can convert and calculate the number of units of MgNO3 and then convert to number of atoms afterwards. Now, what's a decomposition reaction? So a decomposition reaction is where we start with one reactant, turn it into 2 or more products. And so if I look at the first reaction here, that's a combustion reaction. Now, the first one's not a decomposition reaction because I have 2 things on the reactant side. So even though we're breaking down CH4, it's not considered to be a decomposition reaction. It's a combustion reaction. 2 is what would be best called a combination reaction. So if we combine 2 things into a single product, that's a combination reaction. Reaction 3 is also a combination reaction. And then reaction 4 decomposes one thing into 2 or more. And so as long as we have one reactant, it could be by, we could have a coefficient of 2 or 3 or a greater number in front of that molecule, that's fine. But we just can't have 2 or more different substances on the reactant side to be a decomposition. So we want one thing here going to 2 or more products. And so it should be only reaction 4 is the decomposition. The 3 main reactions out of chapter 3 are the decomposition, that combination, and then the combustion. And then if you go into chapter 4, we have the metathesis, that's 2 ionic compounds mixing to get a precipitate. We then have the acid-base reaction giving us a salt plus water. And then metals into solutions of cations. That is the activity series for the oxidation reduction. We want to start with the more reactive substance producing a less reactive substance during the course of those reactions. So those are the 6 key reactions from our 2 chapters. What's the empirical formula of a substance that has, the empirical formula of a substance is this here, C6H5NO2. The molecular weight is 369.342 AMU. What is the molecular formula? So what I would probably do here is think, well, what's the sort of formula weight of the empirical formula? So I take the 6 times 12.01 plus 5 times 1.008 plus 14.01 for the 1 nitrogen, then plus 2 times 16 gives me 123.1. atomic mass units. And so that's the empirical formula mass. I then can kind of see that this is going to work out to be probably a 3 units of the empirical formula in the molecule. But I take the molecular weight and then divide it by the empirical formula weight of 123.1. I can see that's going to give me 3 units of the empirical formula in that molecular formula. So I need to multiply all these by 3. And then I see that I'm going to get 18 for carbon, 15 for hydrogen, 3 for nitrogen, and then 6 for oxygen. If you weren't sure, if you want to double check, you can calculate the atomic, the molecular weight and see that that's 369.34. We'll skip that step. But if you wanted to double check, you could. And then just a couple more chapter 3 review questions for today. Again, this is from the chapter 3 review packet on the daily quiz area. There's a full key and a full solution manual for the questions we're not going to look at here, so we're just looking at a couple of these. One other question I want to look at today was the formula for mass percentages to make sure we remember how to get an empirical formula. Then from that, if we have molecular weight data, we can get a molecular formula. Remember, the percent by mass data at best gives us the empirical formula, the simplest ratio of the atoms. And so the compounds comprised of these by mass, those are the mass percentages. And so 80% by mass carbon. So we're assuming our compound would have 80 grams of carbon in ratio to 20.0 grams of hydrogen to have 80% by mass carbon, 20% mass hydrogen. And so we're starting with the mass ratio, dividing by their grams per mole of each of those elements, 12.01 for carbon, 1.008 grams per mole for hydrogen. And so that'll give us 6.66 moles of carbon, 19.84 moles of hydrogen. Let's divide both of these by the smaller number. See if we get a whole number. Obviously, that'll give us 1 mole of carbon. I think that's going to give us 3. Close to 3 moles of hydrogen. As long as we're within 0.05, we round. I get 2.98, so that's close enough to round to 3 moles of hydrogen. So my empirical formula, the simplest ratio here, will of course just be CH3. And then we're told the molecular weight is double the mass in the empirical formula, so that'd be C2H6 is the molecular formula. And so that would be ethane. Yeah, so CH3 empirical, C2H6 molecular, ethane would be the name. We probably wouldn't ask you the name on this test, but this is an old question from when we had chapters 1 through 3 together on a test. But the idea here is percent by mass, just go to the ratio of the moles. Remember that this is a ratio, so that's why we're going to divide both by the same number and then multiply both by the same number. So if I divide both, if I divide one of them by 6.66, I need to divide the other by the same to keep the ratio intact. And if I double the one, I need to double the other for the molecular weight and the molecular formula. Let's look at one last review question for today. That's the sulfur plus O2 question here. So sulfur and oxygen combined, that's a combination reaction into SO3. And we're told in a particular experiment, we take a gram of sulfur, a gram of oxygen, we produce 0.8 grams of SO3. What's the percent yield of this reaction? Now, a couple things, like you can't just sum the two masses together as the theoretical yield. It's not that simple. We have to think, well, which of those two reactants is the limiting reactant? So we have to kind of figure out, is the sulfur the limiting reactant or is the oxygen the limiting reactant? And then since we want to calculate essentially the theoretical yield of the product, so we can calculate the yield as the actual yield over the theoretical, why don't I go through 2 different steps of calculating the yield of SO3 that we would get if we consume all of the sulfur. And then let's go through this problem again. If we are converting all of the given O2 into product, so to figure out the yield of SO3, the maximum yield we can make will be the lesser of these 2 steps here that we can work out. And so if I start with the sulfur, it's 32.07 grams per mole of sulfur. And then according to the reaction, for every 2 moles of sulfur that react, assuming there's enough oxygen to react with, we'll produce 2 moles of SO2, or 2 moles of SO3. And then 1 mole of SO3 would be 32.07 plus 16 times 3. That's 80.07. That gives me 2.50 grams. But the key here is I can get that mass of SO3 if I have enough O2 for the sulfur to react with. So there's a big assumption here in allowing this reaction to take place, so that assumes we have enough O2. Well, let's see how much SO3 we get if we react all the O2 and assume we have enough sulfur for it to react with. And then so O2 is 32.00 grams per mole. My balanced equation says for every 3 moles of oxygen that react, assuming there's enough sulfur, we'll form 2 moles of SO3. And of course, 1 mole of SO3 is still 80.07 grams. That only gives me 1.67 grams. So when I hit 1.67 grams of SO3, I've run out of O2. My O2 is at 0. And so I don't have enough O2 to get to the 2.5 grams. So if I want to react all the sulfur to produce 2.5 grams of SO3, I'm going to need more oxygen that I don't have available for the reaction. So sulfur is going to be my excess reactant. We could ask how much of it remains, but that's not asked in this question. We're asked the yield, the percent yield. So if I take the 0.80 grams that we obtained, divide by the theoretical yield times 100%, that's a little less than 50%. So that should be the 48%. So percent yield is just the actual yield we get, divide by the theoretical max yield. So this is our theoretical yield. So the theoretical yield is just the maximum yield you get from the stoichiometry in the problem, applying the concepts of limiting versus excess reactants, finding the limiting reactant. So it's the yield we get off of the complete consumption of that limiting reactant. Okay, again, I hate that we have to move on to new material, but at the same time, hopefully there's a few things in chapter 5 that may help us think about some things in the earlier chapters as we move forward. Usually as we do continue, we do reinforce some concepts from earlier material. And also, you know, we got to make sure to get through the chapter 5 and 6 content, hopefully with time to review like we had for midterm 2. So hopefully we get some time to review ahead of midterm 3 in a couple of weeks. So every 3 weeks we're taking exams this semester. We also have fall break in the middle. So finally we get the fall break next week, Thursday and Friday, no classes. So we'll have one less lecture to prepare us for our next exam. Okay, so again, the lecture slides are up in the lecture slide module if you want to take a look at those. So let's get a quick start here in the chapter 5 this morning. So chapter 5 is on kind of a slightly different topic, because we've been on, the concept of like math into atoms in chapters 1 to 2, into naming and seeing and getting used to some formulas in chapter 2, helping set the stage for some compounds we then saw in chapters 3 and 4, and some reactions in water. Here in chapter 5, we get at a sort of a totally different topic, which is, the heat changes that accompany chemical reactions, and trying to understand why some reactions take place, they're going to give heat off. The surroundings can heat up. We can think of, a Bunsen burner, a stove, something that's hot, giving heat off to the surroundings to heat up a pot of water. So generally, and we may remember some of this nomenclature, but you might remember those are like exothermic reactions give heat off that you can use to heat things up, like a pot of water on the stove. So combustion reactions of flame give heat off. And then other reactions will take place and actually absorb heat. So we know that there are some reactions, like the reactions in a cold pack, when they take place, they actually reduce the temperature of the surroundings, and the reactions when they take place actually will get colder. They'll cause the surroundings to decrease in temperature. So in this chapter here, we have to talk about, well, what is chemical energy? How can we think about the sort of potential energy changes that might accompany a reaction from a fundamental kind of picture? What is the first law of thermodynamics? The idea of it is that energy cannot be created or destroyed. That is what the first law of thermo is. So we'll talk about that, define it more precisely as we go. You probably have already seen and heard about it a little bit. We'll then discuss enthalpy. Enthalpy is the main idea of the heat change. The symbol for enthalpy is H. You might remember delta H. And the symbol for H, I think, goes off of heat. It's the idea of the heat of a reaction. So it's, does the reaction get hotter or colder, or do the surroundings get hotter or colder as the reaction takes place? A thought I want to kind of quickly plant in our minds here today is it's really hard to actually track the temperature of a reaction. So if I have a chemical reaction taking place, let's imagine a really, really simple one, salt dissolving in water. Let's take NaCl, put it in water. The reaction, it's hard to know, like you can't really put a thermometer on the reaction. You can put a thermometer on the surroundings of the reaction, but it's hard to put a thermometer on the reaction. So I said something earlier, like the reaction gets hotter or the reaction gets colder. It's really the surroundings that we would track. The surroundings of the reaction are how we kind of see what goes on during the course of a reaction. So we'll talk about enthalpy, enthalpies of reaction, delta H's of reaction, as you probably have seen before. We find delta H's of reaction from calorimetry, so we'll talk about some calorimetry experiments that we can do to find delta H's for some different types of reactions. We'll talk about Hess's law. Hess's law, you hopefully remember this, although we'll teach everything you need to know, but a lot of these things we've seen before. Hess's law is the one that says, like, if it's A to B has a delta H of plus 20 kJs per mole, let's just say plus 20 kJs in that unit. Then if B to C is delta H is minus 30 kJs, then you can track A to C just by summing these two up. And coming up with A to C has to have a delta H of plus 20 minus 30 of minus 10 kJs. So I'm just, more or less adding the reactions up and then just adding up their delta H's. So just taking plus 20 minus 30 to minus 10. That's the idea of Hess's law. It's like if we can sum reactions up, if we can then cancel out the things that are on both sides on the reactant and product side, we can then balance out a new reaction. We can then calculate the new reaction's delta H. Probably seen things like that before, but that's what Hess's law is. We'll define it more precisely later, show how we can use it to solve some problems and find, sort of the idea, there's some delta H's you can study in the lab, and there's other combinations of reactions you can look at to study other reactions through Hess's law. We'll then define heats of formation so we can tabulate in indices and in data books enthalpies of formation. So you can look at a reaction and take a sum of the reactants and products enthalpies of formation. So you might remember problems where you take a sum of the products delta HFs and then subtract the reactants delta HFs, accounting for stoichiometry. That's heats of formation. And then finally, we'll finish with an idea of how strong are bonds, because what's changing in reactions are bonds are being broken and replaced with new bonds. So we'll see how we can calculate and look at bond strengths to calculate enthalpies or to approximate enthalpies to really see that the reason why some reactions lead to giving off of energy, like combustion reactions. We saw that combustion reaction of H2 and O2 at the start of the semester forming water. Water is more stable. That greater stability energy is what's given off in the form of the flame. It has a lot to do with the relative bond strength. So we'll see how bond strengths play a role in enthalpies of formation at the end of the chapter. So again, just a quick overview to give you a sense of where we're heading. Hopefully, if you recall a few of these things, we fired on the synapses to kind of be prepared for what we're going to see here in this chapter, in chapter 5. Okay, so let's talk about, in the form of equations, of a few ideas of chemical energy or just energy in general that we may or may not have ever seen in maybe physics class or in chemistry class before. So work is the energy associated with putting objects into motion. So energy that takes to put an object into motion, we call that work. So work is the force that has to be applied to move an object a certain distance. So it's a force times distance. And so this could be the work it takes to move a car that has a certain mass times acceleration. We don't get too much into like the physics of this, but that's more for like physics class. But force would be equal to a mass times acceleration. You might get into some thoughts of units where the SI unit of force would be a kilogram meter per second squared. That's what a Newton is. That's the SI unit of force. Not a big detail, but just maybe to get us thinking of different units here and how we might see them. Just thinking SI units of mass is kilogram, distance meter times seconds. And so force is a mass times acceleration. So that's kind of where the units come about for force. And then we multiply that by a distance. So if you take a force times the distance, so you'd have a kilogram meter per second squared for force times the distance. The units there be kilogram meter squared per second squared. And that unit, once you now square the meters, that's the SI unit of energy. This is the SI unit of energy of the joule. So that's the SI unit of energy. So we'll see that unit a fair bit. We'll see it through chapter 6 too. We'll use the idea that 1 joule, 1 J is equal to a kilogram meter squared per second squared. And I just wanted you to contrast that with the SI unit of force. This has the square taking off the meter. So the SI unit of force is kilogram meters per second squared. So now kinetic energy is another sort of equation that we've probably seen this before. So it's another kind of thought of motion is that objects in motion have a kinetic energy associated with them. And so that energy would just be 1/2 mv squared. So 1/2 the mass of the object times its velocity squared. And so again, if we're thinking just units going in, mass of the object in say units of kilograms, velocity in meters per second, square those units, you see here that we get the SI unit of energy out from that equation too. So that would be the SI unit of energy, the joule. In other words, that you get a unit of energy out for the kinetic energy equation. You get a unit of energy out for the work equation. Now, heat is a slightly different topic than motion. You know, heat is getting maybe more at like potential energy, but heat would be equal to, through one equation here, the mass of an object times its specific heat times a temperature change. And so you can sort of think, if I apply heat to an object, it should increase its temperature. If I take heat away from an object, if I have a negative Q, it should reduce its temperature. So a plus Q, oops, that's a G. So if I add heat to an object, that should lead the delta T to increasing. So make Q increase, the temperature should increase. And then if you make Q negative or less than 0, then our delta T should, drop. So I take heat away from a substance, temperature drops. Add heat to an object, its temperature increases. CS here is what we call the specific heat. We'll talk more about that later in terms of solving problems with this equation. But I just want to introduce a couple of equations that kind of link together the ideas of energy, link the ideas of heat. The specific heat, we'll talk about units on it later, but we'll just introduce this equation here for now, that we'll see it later, use it more as we get into the chapter. We'll see a slide on this sort of idea next on the electrostatic potential energy. We've seen this, I think a slide from chapter 1 talked about positive and negative particles repel each other, increase their kinetic energy, increase their potential energy by being brought together. And if you have an oppositely charged set of particles, a plus and a minus, then they have attraction. They decrease their potential energy when introduced. And so the energy of electrostatic, either attraction or repulsion, is equal to an equation. Kappa is a constant. We'll never really solve anything with this equation, so it's just an idea that we get off this equation, that if we take a plus or a minus set of particles, that they're going to lead to a greater energy being brought together. So we're going to increase their energy. We'll see a slide to hopefully, I think it would be the same slide we already saw, but we'll show in a slide that two like charged particles will repel. So we get off this equation, like charged particles repel. And then, opposite charged particles attract. So obviously if we take a plus minus or a minus plus, then we're going to get an attractive force. We're going to get a negative energy out in that process. So we're going to decrease the energy when those particles are brought together. So plus or minus, energy is positive. Plus minus or minus plus, with the sign being thrown in, the energy of attraction is negative, attractive. And again, just down here, that SI unit of energy is the joule, based off the fundamental SI units of kilograms, meters, and seconds. Okay, now let's get into the chapter a little bit more. I just wanted to start off with a couple equations to get a sense of things that we're going to see in the chapter. This slide here is getting at that idea of electrostatic potential energy. And so like charged particles, either a plus plus or minus minus will do the same sort of thing. And so our like charged particles repel each other. And so they're going to have a repulsion. Their energy increases as they're brought together. So they're never going to be attracted together due to that increase in energy. In fact, if you have done something to bring two particles of like charge together, you can decrease their energy by separating them. So if you look at these two particles here, if you allow them to separate, then they release energy through their separation. So if you somehow could get two positive or two negative charged particles to be close to each other, you can reduce their energy by separation. Likewise, if you take two opposite charged particles that are, say, far away from each other, and then bring them closer together, they're going to decrease in potential energy. So these particles far away then start to experiencing an attractive force, a drop in energy as they're brought together. That's their attractive force. So energy goes down for the minus plus or plus minus particles being brought together. And then the opposite thought could be that once we bring together like an NaCl or whatever you want to picture as a plus minus, it's going to take energy to separate. So whenever you have two like charged particles that are experiencing their attraction together, that to separate them would require the absorption of energy. So energy would have to be absorbed by the atoms to separate. We'd have to add the energy back in order to get back to separated atoms. So just the thought, like charged particles, we can actually reduce their energy by separation of those particles if somehow they were brought together in the first place. And then likewise, if you have plus and minus or minus plus particles that have an attractive force, separating them would require energy. We'll see in chapter 8 later that we start to quantify or compare that if you were to look at like NaCl, we can start to make sense of this here, and we'll see this later. If you compare that to like O2 minus, that it's going to take more energy to separate the 2 plus 2 minus because the magnitudes of charge are greater. So the greater the magnitudes of charge, and actually the closer the charges are when they're plus minus, the greater the attractive force, the more energy it's going to take to separate. And so you can sort of start to compare, and again, we'll introduce that more as an idea that you'll see like on tests and to compare in chapter 8, but you can get a sense of it now that as the magnitudes of charge, if you take a look at your energy of electrostatic attraction being proportional to Q1, Q2 divided by D, that if you take a look at the magnitudes of charge and you increase the magnitudes of charge, like what we mean by that is a plus 2 charge is greater than a plus 1, a minus 2 magnitude charge is greater than a minus 1 charge. So the magnitudes of charges here are greater, so they're going to experience a greater attractive force, therefore require more energy to separate. So just an idea, something we'll see later that we can start thinking about now. And also the thought of distance. If I can bring the ions closer together, that's going to increase the energy of attraction. So we can think the magnitudes here. The magnitude of attractive force would be higher the closer I can get the ions together. So if the ions are smaller, it actually gives us a stronger attractive force than if the ions are bigger. Let's go and take our quiz here. Keyword today is orbital. Okay, so we'll get back here into the notes. So the slide here is going to start to get at the first law of thermodynamics, that energy is not created or destroyed, so that when I look at a reaction slide like this, let's start here, that if I have my H2 and O2, and we saw this kaboom take place, that when we take H2 and O2 and have them form a more stable set of products, that energy doesn't just disappear. If it did, then we just would have converted those gases into the liquid water, or the gaseous water as it probably flew away with the heat. But if we could have just turned H2 and O2 into water and just had the energy disappear, nothing would have happened. There would have not been a flame, there would not have been a combustion. The reason why we saw the combustion is that there's a change in energy between the reactants and the products, and it's hard to predict when this will happen, but if you have a big change in energy for a reaction that's going to take place very quickly, then you can probably expect there's going to be a kaboom. So the greater the energy difference you can make between your reactants and products, and the faster you can make the reaction, then you're going to have the possibility of like an explosion or like a bomb event taking place. And that's what happened with that balloon when we put the match to it and we had the kaboom take place. Is all that energy was being transferred from the potential energy. Think of how we had energy stored in these bonds. Those bonds are actually relatively weak. I have energy stored in those bonds so that when I combust, I then make stronger bonds, and that energy that I had put into those bonds is then given off. So you can think of H2 and O2 here as almost like having stored the energy in them that then was released upon the formation of water. So I have like stored potential energy. Then when the flame takes place, we hear the kaboom, the molecules in the room are moving with the sound waves that are created by the explosion. That's the potential energy being converted into kinetic energy. So that's all of a sudden going from the stored energy in our bond strengths to then being converted into kinetic energy, the motion of the molecules surrounding that reaction. We also had the creation of heat. So some heat came out of this reaction. Obviously, if I don't want to put my hand on the balloon, but if I did, it would have been burned. So that would have been the heat from the reaction being transferred onto my hand, which would be a terrible idea to do. But you can sort of imagine that the reaction creates energy that can be used to move the objects in the room, like the air molecules. And it can also be used to create heat, like the flame that we see that can heat something up. And so we also have like heat that can be given off by that reaction. So reactions that take place, we have this idea that there can be heat and work that change as the course of the reaction takes place. And so when we see an equation like this, delta E is equal to Q plus W, that we're going to have like almost like two frames of reference. One can be from the frame of reference of the reaction, one can be the frame of reference for us, the observer, or the surroundings. For the most part, we're assuming usually when we write these things, it's from the perspective of the reaction. So sometimes I like to write this specifically, delta E of the reaction would be equal to the heat change of the reaction plus the W change for the reaction. Now, the idea here is for the combustion reaction, for the specific reaction that we're kind of picturing over here for the hydrogen-oxygen balloon, where we have a decrease of energy as that reaction takes place, our delta E for that reaction is less than 0, it's negative, so energy is being lost by the reaction. Not every reaction has a delta E less than 0. I'm just saying specifically for that H2O2 forming water reaction that we're considering with the kaboom that took place, that we know for that reaction that delta E was negative, that energy was lost by the reaction. And then from what we witness from our eyes is that heat was lost by the reaction because we saw the flame. The flame was the temperature. The flame was that heat that we know it would be hot if we touched it. So heat was being lost by the reaction. Now you may say, well, why is it negative? Well, it's negative because heat was lost by the reaction, so it could be given to the surroundings. So the negative heat lost by the reaction went into the surroundings. So we could think here the surroundings energy, the energy of the surroundings, the SURR is just surroundings. So the surroundings of that reaction have the opposite sign. So the delta E of the surroundings has a positive energy. If I think of the Q of the surroundings, just SURR, that's greater than 0. So the energy that a reaction loses can go into heat or work, or the sum of the two. So we also have the idea that the air molecules were moving. We put the air molecules into motion. We were applying a force to move those molecules a certain distance. And so we also were moving those molecules from the reaction's perspective, just like we were heating them up. So just like we were losing heat to heat up the objects around the reaction, the surroundings, we were losing work from the reaction to move the surroundings away from the reaction. So our W reaction here for this reaction is also negative. Again, it's not going to always be possible to predict the signs or picture what it would mean for Q and W to have a certain sign, but for some reactions we can have a predictive capability or understand what the signs of work are. Let's think of this a different way. Let's think of a similar type combustion reaction like H2 and O2 that might take place like every day, like in a car. So like a combustion reaction of octane in an automobile, we know that the engine gets hotter when you turn it on, so that the reaction of octane burning with oxygen with the flame is producing heat. So heat comes off of the reaction, so the reaction loses heat to cause the surroundings, the engine, to heat up. And then the other thing is the car can be put into motion. So when the car is stopped, put into motion by the combustion reaction, work is being done on the car, so the car is moving, it received the work. So the car has a positive W, so the W for the object going into motion is positive, and then what caused the work to go into motion was therefore negative. There's another slide on this, so we'll come back to this idea here in a moment on what it means to have W negative, but the W negative for this, the reaction is the opposite for the surroundings. So if you can picture, it takes work, like the car received work to go into motion, its work had to be positive. Therefore, what created it to go into motion had to be negative, had to have the opposite sign. So we're just hopefully seeing here that these signs are opposite of each other. Now, we also get into some terminology that is kind of peculiar, and that is the difference between what we call a state function and a non-state function. And that's a really just complicated word for saying that some reactions are the same, have the same value no matter how you carry the process out. So delta E is what we call a state function. So that's path independent. Now, what that means is if you have a process, like imagine a reaction of like H2 and O2 going to water, or like 2A going to 2B or whatever. Just imagine some type of a reaction. What this means is that for A to B, that it's always going to be like, let's say it's minus 10 kilojoules. It doesn't matter how you get from A to B, it's always going to be minus 10 kilojoules. So if A to B, let's say the delta H is minus 10 kJs. That doesn't matter how you get there. Like if you go instead from like A to C and then C to B and cancel this out, my A to B in this process here has to still be minus 10 kilojoules because it should be path independent. So my delta E, I think I wrote H, but let me write delta E since I'm talking E on the slide here, that the change in energy for like an A to B or an A to C and then C to B have to both come out to be the same number, because that's a path independent. So it shouldn't matter how I get from, if I go from A to B, or if I go from A to C, C to D, D to E, and then from E to B, that net I've just gone from A to B, and that change has to still be minus 10. So path independent equations or reactions have to have the same magnitude value. And then also if you flip the process, it has to have the same value backwards. So if I go from B back to A, then I'd have to flip the sign. So that should just be plus 10 kJs. So if you flip a reaction, it has to be the opposite sign, because then you got to be able to flip it and go back and still have it be minus 10 to go back. So there's just all these ideas of the first law of thermodynamics that we're not creating or destroying energy. Then also you can flip reactions. You can go in different orders of reactions and get the same magnitude. That's what you get for path independent functions, for state functions. Now Q and W independently, or like individually, are actually non-state functions. They're path dependent. So that means they're non-state functions. Now, how can that be? Well, let's make a couple analogies. One is that, a certain point here to a certain point in like Cleveland, Ohio, have a certain distance between them. Like we can draw the line, you can even take into account the curvature of the earth if you want, whatever. You can come up with a distance between those 2 points. Now, if you drive from here to Cincinnati and then to Cleveland, that doesn't change the distance between here to that point Cleveland. Here to the point Cleveland has a defined distance between those 2 points. It's not changed by however it is you may go between those 2 points. The total distance you travel, of course, the total distance traveled is path dependent. So if you want to go around a circle a bunch of times and eventually get to Cleveland, it's going to take you a lot longer to get there. More distance will have to be traveled. So heat and work are kind of like the distance traveled equations and functions that depend on how you get from point A to point B. Now, another thought here is that when you have a reaction take place, the combustion reaction I think is a really good example, because in your car, don't do this, but if you just put your foot on the accelerator pedal, what happens to the car? So you're in neutral, car's not moving, your foot's on the accelerator, what does your engine do? It revs up, and then where does all the energy from the reaction go? It all goes into heat. So your engine block will start to heat up. Like I said, don't do this, don't test this, but your engine block will start getting hotter and hotter and hotter, then eventually something's gonna break. So if you do this long enough, eventually some component in your engine will melt because it gets too hot, because all the energy went into Q. So all the energy that the combustion reaction had to give off went into Q. If you had just put the car into drive, then a lot of that heat would not have gone into the engine block. A lot of the energy lost by the combustion would have gone into moving the car. So moving the car will use the energy lost by octane to physically put the car into motion, so that therefore you're not putting as much of the energy into Q. So when you have, like, let's say you're gonna burn a mole of whatever thing gives off 10 kilojoules of heat. It's like you can get 10 kilojoules of Q, 0 of W, or you can get 9 of one, 1 of the other, or 8 of one, 2 of the other. The magnitudes of heat and work depend on how we're gonna use that reaction. So it depends on how we're carrying the chemical reaction out. If we get all heat or all work, or some combination or some value of the two that are somewhere in between. The sum of the two, the sum of the heat and the work are still the delta E. So the sum of the heat and the work have to add together to be the delta E for the process. So the sum of the two are still a state function, but each one independently can have any numerical value. Therefore, are path depend on how we carry out those reactions. It's a very, there's a few other slides that will get at this idea of path independence versus path dependence. So hopefully we're just planting a couple seeds here for a few slides where we can reinforce some of this information. Now this slide over here that I haven't talked about yet shows us that two different examples. One is for a reaction that loses energy. That's the more common reaction. I think that's the really easy type of reaction to envision. That's the one where you go from the H2O2 reactive kaboom, we form the products. Really makes sense on why a reaction would have that set of delta E. But we also have reactions where the final state can actually have a higher energy than the reactants, and the reaction still takes place. We'll see a few examples of this, but there are examples of reaction that take place where the final state of the reaction actually increases in energy from absorbing energy from the surroundings. And we'll try to understand that some reactions take place spontaneously that cause this energy change. And the whole reason why they occur spontaneously, though, we can't really talk about, or at least by topic, we don't address it again until chapter 19 later. Those of you who have seen entropy, delta S, delta G, raise your hand if you remember Gibbs energy, entropy. Probably the AP folks, if you just had regular high school chemistry, may not have seen this. But delta G is the equation that tells you if a reaction should actually take place without an applied external force. We're not going to talk about that here in this chapter, but reactions can occur spontaneously with a positive delta E. So I just want to have that thought that reactions are perfectly capable of taking place that have an energy that goes upward. Not as likely, but the thing that we're going to have is a disorder that's created. You'll see about that later, but you'll see that you're going to have somehow the disorder of the system drive those reactions that are taking place. Okay, this slide here is getting at the sign conventions we were just talking about, so let's talk about this again. So we're thinking about the sign conventions for heat, work, and then E. I'm thinking of E here as my delta E. Q and W are really deltas too. It's like the change of heat from the reactants into the products. So heat and work are really the change of the heat and the work as they undergo a reaction too. But I like to think of delta E as being the change from some reaction of picturing, a reaction like A to B. And then Q and W are just how much heat do we get off of that reaction, or how much heat do we have to put into the reaction for it to take place. And W likewise is how much work was either changed to get out of the reaction or to put into the reaction. So let's try to think again about some of the magnitudes here and what they mean. Let's start with E. So a positive delta E. And again, this is from the perspective of all these of the reaction. Remember how before I was saying you can have the perspective from the surroundings or perspective from the system or the surroundings. This is from the perspective. The delta E positive means that there's a net gain of energy by the system or by the reaction. So the system, to me, is the reaction. So the system can be a reaction that's taking place, H2O2 combining to form water, A to B, some type of chemical reaction taking place is our system. So positive means energy is gained by the system. A negative, less than 0 delta E, would imply that energy was lost by the system. So the energy was lost by that chemical reaction. Now, the heat, I think, is a little bit easier to picture the sign magnitudes for heat because the system that loses heat has the same sign as the system that lost energy. So a system that's losing heat has a negative sign of heat. So the reaction loses heat. Where does the heat go for a system that loses heat? It goes to the surroundings. There's this equation we use a lot. The Q of the reaction to the Q of the system is the negative Q of the surroundings. So for a system that loses heat, it goes to the surroundings. It heats the surroundings up, increases the temperature of the surroundings. So for a Q system less than 0 that's negative means my Q surroundings greater than 0. So whatever the temperature of the surroundings was is going to increase when a reaction takes place within it that gives heat off. So if a reaction is giving heat off, the surroundings temperature is going to go up. Now, for some reason, that's like, we'll see this a bunch in this chapter, and I think sometimes we'll keep coming back to this idea because it's confusing, I think, but for the negative Q, the temperature goes up for the surroundings. But again, it comes back to your thermometer is not on the reaction. It's hard to put a thermometer on what was there compared to what is there. That's what a reaction is. A reaction is an idea. A reaction is what used to be there versus what is there now. How do you put a thermometer on that? Like what was there is not even there anymore. What is there now wasn't there before. So you can't really put a thermometer on that thing. You can put a thermometer on what that thing is in contact with, what's in contact with the surroundings. So have that reaction take place in a container surrounded by water, track the temperature of the water. That's one way you can try to see what's going on. Another thing, you can put the reaction in water. So have the reaction take place in a solution and you can track the solution temperature. Usually the solution is the surroundings. We'll talk about these things as we go. So hopefully we're just planting ideas. So if you're still confused, like we're gonna hopefully keep pushing forward and get somewhere with all this. So let's look at the positive sign, or the positive sign of heat means the reaction absorbed heat. So a reaction that absorbs energy has a positive sign. A reaction that absorbs heat has a positive sign for that heat change. So what that means is, now we're also not saying that if delta E is positive, that Q has to be positive. We're just trying to get the idea that if a reaction absorbs energy, that's the same idea and the same sign magnitude as the reaction absorbing heat. Where did the heat come from? If a reaction is positive, if Q is greater than 0 for a system or reaction, it's greater than 0, where did that heat come from? Does it come from magic, thin air? No, it comes from the surroundings. And so for that type of process, our Q of the surroundings will have to be less than 0 in order for the heat to have been gained by the system. So the heat comes from the surroundings. So the surroundings loses heat in order for the surroundings to gain the heat. So what happens to the temperature of the surroundings? Drops. So if a reaction is taking place and heat's being absorbed by the reaction, the heat of the reaction is going up, but it's taking the reactions, it's taking the heat from the surroundings to take place. So if I touch this reaction, generally it will feel cold. There's a few ways reactions can take place. So we'll have to think a little bit about if reactions that are taking place at room temperature. So if a reaction is occurring in a flask at room temperature and its Q is positive, then it should be taking heat from me, the observer of the reaction, if I were to touch this reaction. We'll see an example in person of this at our next lecture. Now let's think a little bit about the sign magnitudes for W. Again, we were thinking about this before, but I think the sign magnitudes go along with the ideas of delta E negative, Q negative. I saw something fly over there too. That the Q is negative means heat was lost by the reaction. Delta E negative, energy was lost by the reaction. W negative means work was lost by the system. So work was done by the system. What was it done on? On the surroundings. So the work, when it's negative, means we're moving the surroundings. Means we're putting the surroundings into motion. So you put the surroundings of the reaction into motion, that's the same as heating. So think of it like this. A reaction gives heat off, so a reaction loses heat. Heat goes into the surroundings to increase the temperature of the surroundings. Then the energy goes into the surroundings to move the surroundings. So it pushes the surroundings, moves the car, puts the car into motion. So the sign of work for the surroundings would be positive if it was lost by the system. So hopefully you can see the idea of energy and work and heat being all kind of the same vernacular, of being lost by the reaction, lost by the system, being put into the surroundings. And then if we have a positive sign of W, it's hard to imagine what this is, but it's like the surroundings are collapsing inward on the reaction. So we have like a contraction taking place perhaps. We have a car slowing down as one analogy, but that's a tricky one to get a perspective of what that means for a reaction. But it's like a piston moving downward instead of upward onto the reaction. It's a contraction, so it means that the work is being done on the system by the surroundings. So there's a couple pictures down here, and so work being done by the system, moving the system, heat being lost by the reaction, going to the surroundings, those are the negative signs. And then heat coming inward, and then work coming inward have positive signs. Now the tricky part is you can't always determine, it's not always easy to predict if Q is positive or negative. You have to know something. And it also is the case that, that if delta E is negative, Q could be negative, W could be positive, or vice versa. They don't have to have the same signs. It kind of depends on some information and depends on some ways that the reactions are carried out. Let's go back to the combustion reaction, because that's one that I think is really easy to kind of have. We've already thought about this too today. But the internal combustion engine uses the combustion of hydrocarbons. We know those are going to take place with the flame. We know that those should have a heat that's lost by the reaction. So we're asked for the delta E, Q, and W for the combustion reaction. So the delta E of the reaction, these reactions, of course, are losing energy. We have stored energy in their bonds being released. That's why the energy used from these reactions can be put into moving a car. The Q of the reaction is going to be less than 0. Heat is lost by the reaction. The car, the engine, will increase temperature because those are the surroundings. So the temperature of the engine of the car will increase during the combustion reaction taking place within it. And then work can be done by the reaction onto the surroundings. So less than 0, negative. And so the W of like the car, the surroundings, will be greater than 0. It receives that energy so it can go into motion. Now, we can throw numbers in. Let's finish with this numerical problem here where delta E of a reaction absorbs, what is the delta E of a reaction that absorbs 22 kilojoules of heat from its surroundings while doing 45 kilojoules of work on its surroundings. So delta E, Q plus W, absorbs 22 kilojoules of heat. Does that mean my Q reaction is plus 22 or minus 22? So the Q of the reaction, Q of the system is positive. So absorbing is positive, releasing is negative. And so it absorbs 22 kilojoules of heat, and then it does 45 kilojoules of work on the surroundings. Doing work on the surroundings is that positive or negative? That's negative. So work done on the system by the surroundings is positive. If I'm heating the surroundings, if I'm moving the surroundings, that's negative. So this will be negative 45 kilojoules. That'll be my W. So my delta E will be equal to plus 22 minus 45 kilojoules. And so that will give us a value of minus 23 kilojoules. So delta E can be positive or negative where a spontaneous reaction takes place. Q and W can be positive or negative as well. They just sum together to be equal to delta E, thinking about their sign conventions. All right, guys, we'll wrap up here today. I'll see you back here on Wednesday. Good luck on midterm 2.